invitation and the opportunity to speak. Before I get into the details, I would like to quickly give you an overview what this talk will be about. First of all, there will be a part about Habiro Cohomology, which is something that Peter Scholze has come up with. And it's a realization of what Peter calls the infinity 2 category of Berkovich motifs. Realization of Berkovich motifs over the integers. So in particular, this is a global cohomology theory. Global in the sense that we do not fix a prime key and work periodically, and that with all primes at once. Right, and also I will give you a recap on how this construction works in a minute. But just for now, what the goal be for today? Well, the goal will be to explain how this Habiro cohomology can be recovered using refined THH. Okay, so more precisely, I would like to maybe sketch how Habiro cohomology for Berkovich motifs over the rational numbers over Q, and we recovered from refined THH. Okay, and then maybe you could ask, what's this good for? Why should we bother with this other description for Habiro cohomology, especially if this second description only works over Q? Well, there are at least two reasons to do so. The first reason is that this approach actually suggests a modification of Peter's construction. It suggests a modification of the construction at the Hodge-Tate point or Hodge-Tate points. And again, I will recap in a minute why we expect such a modification to occur. So there's a certain issue with Scholze's construction at the Hodge-Tate point, and this approach suggests a way to fix that, which I will hopefully explain to you during this talk. And then the second reason to care about this is, well, if we can plug in Ku, and we also can plug in other ring spectra, and could be very interesting to see what happens then. Let me say, would be interesting. What happens if Ku is replaced? Let's say elliptic cohomology, MU, or even the sphere spectrum itself. And we do have some ideas how to compute things in these two cases, but we do not yet know how to reasonably describe this theory. But this is, in general, this is an advantage of this kind of approach, that basically all the constructions you want to do with this are rather straightforward, and all you have to do is compute things, as opposed to coming up with Peter's insane construction. And we can. Will be the first part of the talk. recap on Habiro Cohomology. For that, I should first tell you what the Habiro ring is. Denote this by curly h, and it's the limit over all integers n by divisibility of, you take the polynomial ring z adjoins some variable q and complete q to the m minus 1. And then there's a second way of writing this. We take the limit over all integers, this time ordered in the usual way, of z adjoint q modulo q Hochhammer symbol qqn, which is defined as follows. qqn is 1 minus q times 1 minus q squared up to 1 minus q to the n. And then what Peter does is he constructs a functor from Berkovich motifs to analytic stacks. Motifs, analytic stacks. Sending x to the Habiro stack of x. And then Habiro cohomology is defined to be the sheaf cohomology of this Habiro stack x. As usual for a cohomology theory with a stacky approach. Yeah, so now I should very briefly sketch how this construction of x Habiro works. And for that, the first thing one notices is that it's enough to describe the construction in two cases. So that's what Aoki shows in his thesis. Namely, his thesis, it's enough to describe what happens for the point and what happens for A1. And for A1, we also need to describe the normed ring stack structure on this. This guy with its normed ring stack structure. Okay, so what does this mean? I mean, ring stack is a ring object in stacks, but normed means that we have a map n from A1 Habiro to 0 infinity. Which is supposed to satisfy, basically it's supposed to be multiplicative and that satisfies the triangle inequality. So more precisely, we want that norm of 0 is 0, norm of 1 is 1. It's supposed to be multiplicative. And it's supposed to satisfy, in this case, even the strong triangle inequality. Okay. Now I have to explain how these two stacks are constructed. So let's start with the case of the basis. So this. I forgot to mention, of course, the target is going to be analytic stacks over the Habiro. That's the name of it. Yeah, but the base is not going to be quite the Habiro ring itself, but instead some analytic variant of that, which is about as follows. So this is going to be the analytic spectrum of ring that equals H analytic, which is defined as follows. H analytic is given by a union or K of power series ring Z joins some variable U with the usual solid structure. You adjoin Q and you adjoin these Q Hochschild symbols divided by cos of Q in such a way that these tend to 0, this then tends to infinity. Okay, so what happens here? Especially what is this random variable U that suddenly shows up? On this U, there's some kind of dummy parameter. What we really want to do is we want to work over the stack of norms. So yeah, in analytic stack, there exists this universal stack of norms. So roughly, that's the universal analytic stack, such that A1 over that stack admits a norm in that way, except that that's not quite true. We have to be a little careful with the norm going from the open interval 0 infinity of the closed one and also triangle. Anyway, so we have this stack of norms, and then it turns out that we have this analytic spectrum of Z Laurent series U with its solid structure. Then we can construct a norm on this guy by saying that the norm of U should be 1/2. So that extended describes a norm on this ring that induces a map from the analytic spectrum to the stack of norms. And it turns out that this map is a cover of the non-Archimedean part of the stack of norms. This cover of the non-Archimedean part. And so what we really should be doing is work over the stack of norms. But to write down constructions, it's convenient to work in this specific eventually everything descends. Okay. So this is why this parameter U somehow appears. And then what do I mean by this? By this I mean that I adjoin these quotients QQN over U to the K times N as a null sequence. Adjoin as null sequence, which is something that I can do in this world of condensed mathematics. And so in total, what this formula is supposed to mean, it's supposed to mean that H analytic is the initial series U Q algebra such that all I think better way to say it's not adjoint, it's a null sequence because we already have these elements. This so I want to make the null sequence. But I really want by that is that this is the initial algebra such that these cube Hochheimer symbols decay faster than any exponential. Okay. Faster than exponentially. So that's achieved by making these guys into null sequences for okay. All right, and then one can check that there's really a map from H into H analytic. Okay. So that's the base case. And then there's the case of A1. And for this, I will instead describe what happens for GM, because A1 Habiro is then in the end ballooned from two copies of GM Habiro along GM without no Habiro. Okay, so now what's GM Habiro? This is given as we take the analytic GM over the analytic Habiro ring, and then you mod out by the subgroup generated by all X, such that again some condition like above is true. So we want that X Q n divided by U to the K times n goes to 0 as n goes to 0, goes to infinity. For all K. And here this cube Hochhammer symbol is defined as follows. So xqn is 1 minus x times 1 minus 2 times x, dot up to 1 for the acute n minus 1 times x. Okay. Yeah, so roughly we are modding out by the subgroup of all x, such that these cube Hochhammer symbols x comma q to the n decay faster than exponentially. Right. And then there's a bunch of stuff that I'm not telling you, specifically how this gluing works. That's one of the hardest parts of the construction and one of the reasons why we really need all this setup with the analytic ring and all that. And I'm also not going to tell you exactly how the ring stack structure and the norm works, but I wanted to have this formula on the board anyway, in any case, because this is precisely where we see this issue at the Hodge-Tate point showing up. So what is this all about? We have the following remark. So if we specialize Q to 1, which is something like the Hodge-Tate point in the setting, Okay, what happens then? Well, then this Q Pochhammer symbol x comma q to the n is just going to be the power of 1 minus x. And then this subgroup here is just going to be the overconvergent neighborhood of the origin, the origin of 1. So we get that Gm Habiro specialized at q equals 1 is just Gm analytic over the set the wrong series u, and then modulo an overconvergent neighborhood of the unit. Okay, and then this implies more generally that if you take Peter's Habiro stack and specialize at q equals 1, then you just going to see the analytic, the RAM stack. And that object is pathological in characteristic P because we are taking an overconvergent neighborhood and not some kind of overconvergent divided power neighborhood. Really just the overconvergent neighborhood, and then this is pathological in characteristic P greater than 0, but also in characteristic 0, it's not what we would expect. Because we should rather expect to see some kind of de Rham to Hodge degeneration at the Hodge-Tate point. In characteristic 0, we don't see Rham to Hodge degeneration. Okay, and this refined THH approach will not tell you anything about characteristic P because it works for motives over Q. But this modification here in characteristic 0 should be provided by this other approach. And also something similar happens if I specialize at other roots of unity. Similarly, at q equals zeta then. Okay. Then let's explain what we find THH is.
Is there supposed to be like a non-analytic version of this instruction where I get something genuinely stacky? So, am I understanding correctly that GM Habiro is the chief of sets?
I think so. I think that's an actual subgroup, and that's like part of the problem. So when I put q equals 1, it's still going to be a subgroup, and I don't want that.
But is that related somehow to the fact that this was like you're working in some analytic theory where there is this U, which is topologically nilpotent, and I should only be seeing the stackiness as allow U to become 0, or is that not the right picture? Sorry, I'm just.
No, this U is never going to be allowed to be 0 because so it's you have this stack of norms, and say you have an analytic ring with a norm, then locally in this Schwick topology you can always find a unit of norm 1/2, and that's basically what this extra parameter U does. And
I guess I'm sorry, maybe I can ask later, but I'm wondering if there's a version of this construction which makes sense over Z power series cube rather than Z Laurent series cube.
You want to see formal schemes and not just generic fibers of formal schemes as things that are.
Right, but I'm also wondering if the fact that this is a sheaf of sets is related to that.
Okay, maybe we should discuss this afterwards. Thanks. Oh, yeah, but thank you for the question. Okay, so yeah, maybe we first tell you what this construction is supposed to do. So as you probably all know, THH is super useful for, let's say, formal schemes over ZP, because then you can use it to construct prismatic homology. But in a rational situation, so let's say for some rigid analytic variety or something, it cannot be too useful, because whenever you put in something rational into THH, it's going to be the same as usual Hochschild homology, and so it can never see more than Hodge-Tate information. However, this refined version of THH has the amazing property that you can plug in rational objects and get out something that's no longer rational. So you get out something that's non-trivial modulo any prime, which we are going to see. So how does this construction work? This due to Efimov, of course, and Scholze. And for that, let me fix some E-infinity ring spectrum K. And then I can look at THH relative to K. So this is a symmetric monoidal factor from localizing motives over K to the category of modules over K with an action of the circle. And then it turns out that this category of localizing motives is rigid. That's one of the amazing things that Sasha proves. But this other category here is not rigid. And I'm going to recall in a second what rigid means. Just let me get to the punchline. So since this is a factor from something rigid into something non-rigid, just by abstract nonsense, we get a factorization through the universal rigidification. So through mod K BS1 rigidified, and that factorization is refined THH. We briefly recall what these motions.
That board doesn't move.
I'm now afraid of this one. What does rigid mean? Let's say we have a presentable stable symmetric monoidal affinity category. the category C. It's rigid if two conditions are satisfied. So first of all, the tensor unit needs to be compact. And the second condition is that C is generated under colimits by a certain object, certain objects. So C is generated under colimits by objects that are themselves colimits. And objects of the form these are sequential colimits. 0 to x1 or not, such that each transition map is what's called trace class. That each and xn plus 1 is trace class. Okay. Then I should probably also remind you what trace class means. So morphism phi from x to y is trace class. If there exists some morphism eta from the tensor unit to x dual tensor to y. Is also another.
Waited for this for 3 years.
And if you want to do the other stuff, I can drop it again just for you. Yeah, that one was really convenient. Okay, so there exists some eta from the tensor unit to x dual tensor y, where x dual is the internal hom from x to the tensor unit. And I want that phi is the following composition. So I can go from x to x tensor x dual tensor y. And that morphism here is just x tensor with this eta. X tensor eta. And then I can evaluate in these two components and get back to y. Evaluation tensor y. And the composition should be y. Should be phi. Right. Okay. Yeah, so that's what rigid means, and that's what trace class means. It turns out that in this specific situation, we have an explicit description of what the rigidification is. So namely, it's what's called the nuclear int category of K modules with the circle action. What's the lookup that I should recall? Namely, the nuclear int category some C inside sits inside the int category, and it's generated under colimits by certain int objects, namely by int objects that look as such. It's generated by int objects of the form an int colimit of x0 was 1 dot dot dot, such that each transition map is trace class. 2x and plus 1 is base class. And just a word of warning, on first glance, it looks like the nuclear int category would be the rigidification in general, but that's not quite true because the xi here are from C and not necessarily from nuc int of C. However, in this specific case of K modules with a circle action, or more general for locally rigid categories, this nuclear int category is always the right rigidification. That's again something that Sasha shows. Right, so that's the construction of refined THH. And there's a modification of this construction that that's also got in the relevant. So in the case where K happens to be complex orientable and we choose a complex orientation, so we now assume E in phi minus 2 of KHS1 is some complex orientation. So in that case, it turns out that K modules with an action of the circle is equivalent via the factor of taking homotopy fixed points to modules over KHS1, which are T complete. And then, of course, you get an equivalence on rigidifications. This is the same as nuc int of that category. So modules H1 T complete. And then the composition of refined THH with this equivalence is refined TC minus. TC minus refined.
So here in this generality, do we really not need a Q index colimit like that on that board?
Yeah.
Yeah.
Here it's fine. But you're right that the rigidification in general is given by a version of this nuc int category where the int objects are no longer indexed by the natural numbers, but instead by the rational numbers. But yeah, this is this is this difference between the xi being from C and from nuc int of C. There are a few remarks I wanted to make about this construction here. So it turns out that this construction is quite flexible. Because we have at least two ways in which we can modify it. First of all, we can vary the target category, which in this case was told to be K modules with an action of the circle. But in some cases we can do better. So for example, if our K happens to be the sphere spectrum, then THH admits a cyclotomic structure. So we could also take cyclotomic spectra as a target, and then the refinement would take values in the nuc int category of cyclotomic spectra. could use cyclotomic spectra. And then another case, which is going to be very relevant for us, is the case where K is KU. So in this case, we can't quite use cyclotomic spectra because KU is, as far as I know, not a cyclotomic base.
So cyclotomic spectra is not locally rigid.
It's not?
Is it?
I think it is.
It is, really?
Yeah, I think it's or maybe okay, maybe I should think about this again. But I mean, we can still look at the refinement.
If you chaotically complete, then I think or well, maybe. Okay, anyways.
In any case, the category that I'm now going to tell you about is going to be locally rigid. Because in the case of KU, it turns out that THH relative to KU still carries what's called a cyclonic structure, and cyclonic spectra is locally rigid. In this case, we can use cyclonic spectra. Okay, what does cyclonic mean? Maybe not give you the complete definition, but roughly cyclonic means S1 equivariant. But in addition, there's this notion of a genuine equivariant spectrum in genuine equivariant homotopy theory. And we want genuine equivariant structures for all the finite subgroups of the circle. And these also should be compatible with each other. So it should be S1 equivariant plus you want compatible genuine, well, let's say upgrades of the action of CM for all finite cyclic subgroups. Subgroups CM of the circle. And then the second thing we can do, of course, is we can also vary the source of the construction. For example, one thing that one can do is you could look at absolute THH, but you only accept modules, motives that say over ZP as an input. Then and the spectrum with circle action. And we'll refine that further. And the result of that is going to be quite different from what you get if you refine absolute THH, where you allow all the nothing motives as input. This THH defined as up there. In particular, this guy is really hard to approach, but this guy here is a little bit more computable, and it seems to be somewhat related to analytic prismatization. And moreover, we don't really have to restrict to the case where we look at localizing motives over some ring spectrum. We can look at more general cases, which is also going to be relevant. This is another part of what Sasha shows is that localizing motives over any base category E is rigid if E itself is rigid. And so there are many more bases that we can use, except rather than we don't have to restrict to ring spectra. We can also pack in more general categories here. And that again is going to become relevant in a few minutes. Because now I would like to show you a few constructions and then finally a few computations and then finally sketch what this refined THH has to do with Habiro cohomology. This is going to be the first and final part. The first computation I would like to mention is this some joint work that I did with Samuel Meyer. We computed what we find TC minus of KUP completed tensor with Q relative to KUP completed is. And then the homotopy groups of that. Right, so in particular, this is one of those cases where we plug in something rational. And as we will see in a second, the result is very much not rational. Yeah, well, maybe the result is we get the ring of overconvergent functions on a certain Z, which I'm going to find in a second. And then adjoint the odd element to the plus minus 1. Now, what is this Z? Oh. Well, maybe write this completely out. This O of Z dagger. It's overconvergent functions.
What does pi star mean here? Like the output lives in this funny category, right?
Yeah, it's the output lives is in this nuclear int category. So I can look at the int homotopy int groups, and these turn out to be nuclear again. And let me maybe, yeah, these turn out to be nuclear again, and then I can, by another result of Efimov, identify them with certain solid abelian groups, and that's what I'm going to use here. So let me maybe write down what this dagger is, and then come back to this point. So these are going to be overconvergent functions. On this Z. This lives inside the adic spectrum of ZP power series 2 minus 1. And this adic spectrum, you can usually draw this, or people usually draw this as some kind of plane with a P axis and a Q minus 1 axis. And then what is the Z? So first of all, you have to restrict to the analytic locus. So you remove the non-analytic point at the origin. And then Z consists of the locus where Q is 1, the locus where Q is a p-th root of unity, the locus where Q is a p-squared root of unity, and so on. Then these loci converge to the locus where p is equal to 0, which is also included. And then we take over convergence functions on this funny Edding space. And then to come back to your question, this ring of overconvergent functions is, I think, best described in this formalism of Clausen and Scholze. So it's going to be some solid ring. And in fact, it's a nuclear solid ring. And then there's a result of Efimov that says that nuclear solid embeds fully faithfully into nuclear int. And if I regard these homotopy groups as nuclear int objects, they can then through this fully land in the essential image and can then be identified with this kind of object here. Yeah, so in particular, this Z contains the locus where P is 0, except for the point at the origin. And this is telling us that the modulo P is non-zero. And so in particular, what I said, that in general, if you take this refined THH or TC minus construction and plug in something rational, it can very much happen that the result is non-trivial modulo some preps. Okay. So that's.
Is that also true of refined THH or only refined TC minus?
I mean, refined THH and refined TC minus contain the same kind of information, right? And so if
But the state refined THH would be acted on by the original thing, so it would not be possible for that to be non-rational.
no, if you get the original thing, if you take the colimit and complete. So this, in this case, the way to think about the well, maybe if we pretend for a second that this nuclear int category could be identified with some kind of nuclear solid category, then the underlying object that you're talking about would be the T completion.
Sorry, are you saying that it is or is not a phenomenon that also happens for THH?
I'm saying it is a phenomenon that also happens for THH. Maybe we should also discuss this afterwards. Right, because now I have like 8 minutes left to talk about Habiro cohomology. Okay. So how do we recover Habiro cohomology? For that, let me first define the following object. I'm not sure if this has a name already. If it has, please tell me. But I'm going to call this the topological cyclonic homology. And it's U. And this is supposed to be, you start with topological cyclonic relative Ku. So what is this? You start with THH relative Ku. And as I said before, this has a cyclonic structure. In particular, it has a genuine CM equivariant structure for all finite cyclic subgroups. So I can take genuine fixed points. Then I can take homotopy as one modulo CM fixed points. And then I can take the limit over all them. And I think if I would not take the homotopy fixed points here, that would just be TR. But I want to take the homotopy fixed points, and then I don't think that has a name already. Right. What's this object supposed to be? So in general, in genuine equivariant homotopy theory, genuine fixed points often behave like a sort of decompletion of homotopy fixed points. And that's precisely what we are going to see here. So if we would take homotopy fixed points all the way, this would just be TC minus, and the object that we would get would be Q minus 1 complete. But since we have the freedom to take genuine fixed points here, we get some sort of decompletion, and then the object in the end will be one of these Habiro-like objects. Right. And then I want to construct a refined version of that, which can be done by varying the target to be cyclonic spectra. Define THH relative Ku and localizing notice over Ku to Ku modules in cyclonic spectra. Get some refined version of this topological cyclonic homology. Topological cyclonic refined. And then that's going to be the object we are looking for. What do we know about this object? Okay, let me first show you how you can get the analytic Habiro ring from that. Theorem. I'm pretty convinced that I have a proof for that. Let me maybe for safety reasons put them in progress. So namely, if you look at topological cyclonic homology refined of take U, the joint sum Laurent series variable relative to, and here I take nuc int of modules over Ku, and here I really take the power series ring, which are U complete. So I can do that because this nuclear int category is rigid. And so by this remark about varying the target, varying the source of the refinement construction, I can do this. And then again, compute pi star of that. And that's going to be analytic Habiro ring element. Okay. And then how do we get Habiro cohomology in general, at least? What we want to do in general. Let's say for a Berkovich motive X over Q, and then I can always make sure that it really lives over Q on the four series ring. I can look at reasons that can be very weak version of the even stack of homological cyclonic refinement of KU tethered with nuclear sheaths on X relative the guy up there. I forgot to invert U on the outside. And then let me quickly say what the expectation for the value on GM is and how this fixes this kind of problem that we are seeing here.
You're inverting U on the outside of the parenthesis one. High star with U inverted, or?
I mean, that shouldn't matter, right? So I take this topological cyclonic object. This is going to be some nuclear int object, and then I invert U. It doesn't matter whether I do that on that object itself and then take high star or okay. Almost out of time for expectation. Again, I think I have a proof for that, but safety reasons, we call this in progress and an expectation. So for GM, what we should get is the analytic GM modulo the subgroup of OX such that if I take X Qn divided by QQn, then the absolute value of that would be at most 1. Now, if you compare that with the construction on the other side, we definitely have a map from here to surjective map. GM 0, which was defined to be GM analytic modulo basically all X such that X comma Qn decays faster than exponentially. Right, because in our base Qn decays faster than exponentially, so this conditional definitely applies this. Decays faster than exponentially. And I would think that this is precisely the modification that we were looking for. That has the effect that once I specialize Q to 1 or to any root of unity, you are no longer going to see subgroup being modeled out, but it's going to be some proper stacky thing. And we're going to see, hopefully going to see precisely the round towards degeneration happening there. Okay, I'm very much out of time, so let me thank you.
Question. I have a question. So in this for the general is it doesn't seem clear to me that even in the case X is a point that these two formulas are the same. It's because it seems like the category KU tensor nuke X is rational.
Right. Okay. Yeah, so what happens here is I didn't specify the base here, and the base is not going to be the analytic Habiro ring. It's going to be well, the Habiro stack of Q, and the Habiro stack of Q is I mean, these two are not supposed to be the same, right? So this is the Habiro stack of the integers, and here we are only, as our base, only going to see the Habiro stack of Q.
Okay.
And yeah, maybe I should. Okay, maybe let me put.
Oh, I see. So it's
Habiro here.
rational for okay.
And
Okay.
because I have to base change to be over here as well. Yeah, so as I said, this approach will only ever recover the rational part of Habiro cohomology. Hopefully already does. Something interesting.
What's the role of KU in what you're describing? It seems like you didn't use anything special about KU in everything that you said.
Okay, I think. So what's special about KU is that I can actually compute what that is. So as I said, we have some ideas how to do that for elliptic homology or MU, but couldn't complete the calculation so far. So yeah, but it seems like you could very much put another base there and see what happens.
Do you expect that if you put something else there, you would see basically the same answer with some extra parameters, or do you expect to see something genuinely different?
That's a good point. So one thing about if you put higher chromatic spectra, this refined TC minus or whatever I construct here, it will always vanish after K n localization for n at least 2. But that doesn't mean that if I put something like elliptic homology or MU there, it's just going to be the same answers with a few more parameters. This has something to do with the fact that if you regard these nuke int categories as some sort of nuclear solid categories, then there are several ways of localization. We can algebraically invert some parameter like V1, which would correspond to like imposing the condition that the absolute value of V1 is at least 1. Like algebraic localization in the world of adic spaces would look like. But you could also allow for V1, the absolute value of V1 to arbitrarily small but non-zero in maybe relation to some other parameter. And in the case of elliptic homology, already in the case of elliptic homology, that's what should be going on.
Can I ask a question? No?
Sure.
So I'm wondering if there is a precise candidate for the extension of the magnetic spectrum of the Habiro ring to stock norms, and whether we can see also via refine localizing. I mean, I want to also cover the Archimedean.
I don't know. I mean, you can try to impose this condition that the two Pochhammer symbols decay faster than exponentially, also on the Archimedean branch. I don't know if that yields something.
Definitely, you cannot take like solid, right? So.
Yeah, okay. But instead of then replace this Laurent series U by you had ±1 gaseous. And then do the same kind of construction. I don't know if that works, but
did you try to see why this refine localizing? Right?
I'm not sure if that makes things. I think in this refined picture, I would be struggling to find a replacement for a category of U complete modules over KU count series. But it seems to be that there's an Archimedean side to Habiro Cohomology, to this weird relationship to Chern-Simons theory, but I know very little about this. It's still very, very mysterious. Yeah.
Oh, sorry. So at the very end, you said that with this modification of the Habiro stack, you could somehow see the generation of the Hodge-Tate spectral sequence. Could you maybe say a bit more about this?
The best way of saying this. Right. I think that's a little subtle. Okay, I can say as much. You can do everything except this topological cyclonic guy with the small KU as well. I mean, you can. Sorry, let me maybe try to write that something down. I think what you're asking, if you really want to see the Hodge-Tate spectral sequence deformed in some way, then you should be looking at EC minus refined of something relative to the connective K. And if you specialize that at Q equals 1, or more precisely at data equals 0, then you're going to see something like HC minus refined relative to that. And that's so the base of this is not quite A1 modulo GM. It's some overconvergent version of A1 modulo some version of GM, and then over that you can really see some kind of Hodge-Tate specialization degenerate right to Hodge degeneration. I'm sorry, maybe we can discuss this afterward, and I can make it a little more precise. yeah, I guess in this Habiro picture, you know, I think I'm right now I'm getting confused. Maybe we should really discuss some of those.
Let's thank Ferdinand.